Hi everyone, in this video I will be showing you my implementation of Marching Cubes. If you don't know what Marching Cubes is, it's an algorithm that turns a mathematical scalar field into a mesh. It processes a group of cells one at a time. The code to process one cell is on Paul Bork's website, as you can see. Basically, to process one cell, it takes the density values at each corner and generates an 8-bit case code. Then it makes a vertex at each edge where there's a sign change. Finally, it connects these vertices using a lookup table to make triangles, which creates a mesh. So a naive implementation of Marching Cubes would be a triple for loop. One loop for the x, y, and z axes. The innermost for loop runs the algorithm shown on Paul Bork's website, which just processes one grid cell. The problem with this is it creates duplicate vertices. I'll show you an example of this in Paint. My version of the algorithm solves this issue by splitting the algorithm into two phases. Well, technically three if you include the scalar field generation, which is done here. It fills a multi-dimensional array of sign bytes with density values and normals at each vertex of a grid using a function, such as the torus function shown up here. Thanks, Lynn, for providing that. Lynn is also working on a Marching Cubes algorithm, so yeah, he kind of inspired me to make this video. Anyway, I'll start by demonstrating the algorithm in Unity. The first phase is the vertex generation phase. The input is a mathematical scalar field of density values, as I said, and the output is a list of vertices, along with an integer array of edges that maps an edge to a vertex ID. I decided to make the scalar field of density values made of sign bytes, as they are much smaller than integers and greatly reduce the memory footprint without causing too much of a quality loss. Anyway, as you can see here, it starts with the triple for loop. In the innermost loop, 3 edges are processed at once. I'll show you what that looks like in 2D in Paint. The first thing that is done is it checks if the density at the x, y, and z of the for loop is 0. If it is 0, then that point lies on the surface and a vertex can be created at that point, and the set of 3 edges can be skipped. Without this if statement, 3 vertices at the same location would be created, wasting memory and time. The next thing that happens is it checks to make sure that the line segment forming the y edge is entirely within the field of density values. Otherwise, we would get an out of bounds error, as you cannot use a negative value as an index of an array. Once the line segment is confirmed to be inside the field of density values, the second density value of the edge is retrieved. With the 2 densities of the endpoints of the edge, you can check to see if there is a sign change by checking to see if the last bits of the density values are the same. If the second density value is 0, that means a vertex at this position was already created and it can be reused, as you can see on line 61, where the vertex ID of an adjacent edge is reused instead of making a new edge, or a new vertex. If not, though, a new vertex needs to be created. This is done by linearly interpolating the vertices based on the density values. The normals are also interpolated and generated in this part. This process is repeated for the x edge and z edge. Once that's done, the triangulate function is called. The first part of the triangulate function is very similar to Marching Cubes. It iterates over each cell, creating a case code for each one based on the density values of the corners. Note that I didn't use an offset table, and instead hard-coded the offsets. As much as this reduces readability, I discovered that this resulted in a small increase in performance, so it is worth it. I could have used a similar for loop to generate each edge in the generate vertices function, but unrolling the loop yielded better performance. Anyway, back to the triangulate function. After the case code is generated, and if it is not 0 or 255, which means that the cell is entirely in or out of the surface, a set of 3 edges containing the vertices that make a triangle are retrieved in the variable mc_edge. This value ranges from 0 to 11, where each value corresponds to an edge in a cube. Using this value, a lookup table I made, and the x, y, and z coordinates of the cell currently processed, I mapped this value to an index for that massive edges array that was created in the generate vertices function. Plugging this index into that array yields a vertex ID. As long as these vertex IDs are not the same, then a triangle is created. If they're the same, then that means the triangle has 0 area and can be ignored. That's basically it. It's not the most revolutionary version of Marching Cubes, but it does contain optimizations that greatly speed up the original algorithm, while also reducing the vertex and triangle count. Subscribe if you want more videos. I'm going to be going over level of detail with this Marching Cubes algorithm in my next video. Thanks for watching.